Welcome back to The Explainer. Today, we're jumping right into the invisible engines that make deep learning actually work, activation functions. We're going to trace this really fascinating evolutionary tale of math, where basically every brilliant solution accidentally created a fatal flaw, and then engineers had to scramble to fix it. It's a fantastic story of trial, error, and just absolute mathematical elegance. Let's dive in. Here's a quick look at our roadmap for today. We'll start with the brain's spark, move into linear limits and vanishing gradients, explore the ReLU revolution, look at curing the dying neuron, and finally, the final output. We'll be tracking exactly how each function solved the fatal flaw of the one that came before it. All right, section 1, the brain's spark. So our very first attempt at an activation function was actually super intuitive. It was this naive binary step function. Basically, when an artificial neuron calculates the weighted sum of its inputs, it needs some kind of mechanism to decide whether to fire, right? So the logic was simple. If the input is above a certain threshold, boom, the neuron fires at a solid 1. If not, it stays completely off at 0. It's literally like flipping a light switch. But this has a massive problem. It's totally rigid. Because of that sharp vertical jump right in the middle, it's not differentiable. And without a smooth derivative, backpropagation just doesn't work. The network literally cannot learn from its mistakes because it has absolutely no idea how to adjust its weights. Which brings us to section 2, linear limits and vanishing gradients. Engineers quickly realized they needed something smoother. We needed analog values, not just a binary yes or no. So enter the simple linear activation function. As the input goes up, the output goes up, right along with it, proportionally. This gives us a constant gradient, which is awesome because it means backpropagation can actually do its job, the network can adjust. But solving the learning problem introduced a completely new, massive architectural disaster when we actually tried to build deep networks. We fell into what's called the linear trap. Here's the fatal flaw. If you use a linear activation function, it literally doesn't matter how many hidden layers you stack on top of each other, mathematically. The entire network collapses down to be perfectly equivalent to just one single layer. You completely lose the depth in deep learning. Without nonlinearity, your massive complex neural network is completely incapable of learning complex nonlinear patterns. You've essentially just built a giant, really expensive calculator doing basic math. Enter the absolute hero of early deep learning, the sigmoid function. This beautiful, smooth S-curve was a total game changer. It cleanly bounds our output between 0 and 1, and crucially, it's entirely nonlinear, meaning we can finally stack those layers and create truly deep networks. Plus, it has a nice smooth gradient for backpropagation, so problem completely solved, right? Well, not exactly. Let's look at sigmoid's villainous side effect, which is the vanishing gradient. If you look at the far left or the far right of that S-curve, it flattens out almost completely. In those flat regions, a change in the input produces practically zero change in the output. And when that happens, the gradient, which is the crucial signal telling the network how to learn, just vanishes. It fades away. The learning process practically freezes in its tracks, and the network either drastically slows down or just outright refuses to learn anything else. So engineers try to patch this up with the tan function. Tan is basically just a scaled version of sigmoid. It bounds outputs between -1 and +1, which is actually brilliant because it centers the mean at 0, helping the weights converge a lot faster. It also gives us a steeper, stronger gradient right in the middle. But at the end of the day, it's still an S-curve. If you push those inputs too high or too low, the gradient still vanishes. The network still stalls out. Which brings us to a massive pivot point in the history of deep learning. Researchers were faced with this huge question. How on earth do we keep the gradient strong, maintain nonlinearity so we can actually stack layers, and keep the whole thing computationally efficient without our signal constantly fading away at the edges? And that kicks off section 3, the ReLU revolution. The answer to that question triggered a total paradigm shift. I'm talking about the rectified linear unit, universally known as ReLU. The math here is almost laughably simple. The output equals the maximum of either 0 or x. Positive inputs just pass right through linearly, and negative inputs hit a brick wall and become a flat 0. Now, you might be thinking, wait a second, didn't you just tell us that linear functions destroy deep learning? Well, yes. But the genius here is that while one ReLU is linear on its own, combinations of multiple ReLUs interacting together become highly nonlinear. Plus, because it's just basic threshold math, it is extraordinarily fast and highly computationally efficient. But here's the real magic, its absolute superpower,
sparse activation. Because ReLU forcibly outputs exactly 0 for any negative input, if you look at a randomly initialized network, roughly 50% of your neurons simply won't fire at all. They're completely deactivated. Instead of every single neuron calculating complex analog values all the time like they did with sigmoid, ReLU creates a sparse network. And fewer neurons firing means massive, massive savings in computational power.
But keeping with our evolutionary theme here, this brilliant solution birthed a tragic new problem: the dying ReLU. That flat 0 line on the negative side, well, it has a gradient of exactly 0. If a neuron's weights get updated in such a way that it starts only receiving negative inputs, it gets pushed into this flat zone forever. It outputs 0, its gradient becomes 0, and it never updates again. It permanently stops responding. The neuron essentially dies, becoming useless dead weight taking up space inside your network.
Which leads us perfectly into Section 4, curing the dying neuron. Naturally, engineers weren't just going to sit back and let their networks die. This sparked the era of the fixers, these clever little mathematical tweaks designed specifically to revive dead neurons. Enter leaky ReLU. It's honestly an elegant little hack. Instead of a totally flat horizontal line for negative values, we just tilt it. Just a tiny bit, maybe multiplying it by 0.01. By providing this tiny incline, we ensure the gradient is never perfectly 0. Some incredibly small amount of error signal can still leak through, which gives a technically dead neuron a fighting chance to slowly learn its way back to life over time.
Then things got intensely mathematical with SELU, or scaled exponential linear units. The sheer mathematical wizardry at play here is wild. It acts as a solution to a fixed point problem. It's specifically designed to automatically preserve the mean and variance from the previous layer. This creates what's called internal normalization, baked right inside the activation function itself. Because of this native normalization, SELU mathematically prevents the dying neuron problem entirely. It's an incredibly robust, self-stabilizing system.
Finally, Section 5, the final output.
So think about it. We've carefully managed nonlinearities, we've dodged vanishing gradients, and we've resuscitated dead neurons through hidden layer after hidden layer. But eventually, all this raw mathematical energy hits the final layer, and we need actual humans to be able to understand it. That is where softmax comes in. Softmax is the ultimate closer. It takes the raw, multidimensional outputs of the network, these are often called logits or energies, and elegantly squashes them. But unlike sigmoid, it squashes them proportionally across all the outputs so that they all add up to exactly 1.0. It turns abstract network energies into a clean, highly readable final probability distribution. It's the function that finally lets the network confidently say, hey, I am 95% sure this image is a cat. And that brings us to the end of our evolutionary tale. We started with a brittle step function and arrived at these incredible self-normalizing probabilistic engines. But honestly, it leaves us with a pretty fascinating thought to consider. If every single activation function we've looked at today was essentially just an engineering patch for the spectacular failures of the last one, what invisible, fatal flaw is hiding in today's absolute state-of-the-art networks right now? And more importantly, what is tomorrow's next great equation going to look like to fix it? Thank you so much for exploring the math with me on this explainer. Keep asking questions and keep learning.